Now, there are three different ways in this class that we're going to define the so-called 6 trigonometric functions of angles. The first one we're going to look at, and probably the most familiar to you, is the idea of a trigonometric function as a ratio of sides of a triangle. So in this treatment, we're going to think about theta, which is going to be an angle, as being one of the acute angles in a right triangle. So being in a right triangle, theta has to be greater than 0 but less than 90 degrees. So if we have a right triangle, we of course have 3 sides, 2 legs, and a hypotenuse, and we will label these sides as follows. The side that is opposite our angle theta, I'm going to label with OPP for opposite. The leg that is adjacent to theta, the one that actually contains theta, we're going to label ADJ as adjacent. And finally, the hypotenuse we're going to label as HYP for hypotenuse. So with the 3 sides labeled like this, there are going to be 6 different what we'll call functions of theta involving the ratios of sides of this triangle. So the first 3 we call the sine, the cosine, and the tangent of theta. Okay, and the sine we're going to denote by sin theta. The cosine will denote by cos of theta, and the tangent will denote by tan of theta. And the sine of theta is going to be defined as the length of the opposite side divided by the length of the hypotenuse. The cosine is going to be defined to be the length of the adjacent side divided by the length of the hypotenuse. And the tangent is going to be defined to be the length of the opposite side over the length of the adjacent side. So these are our 3, these are sometimes called fundamental trigonometric functions because the other 3 are going to arise by taking reciprocals. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. There are a number of mnemonics that you can use to remember these relationships. One of the most common ones is the mnemonic so, ka, toa. Okay. A lot of high school students learn this one. And this just reminds you that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. You can also use little phrases like some old horse caught another horse taking oats away. That one's a little corny, but it works. If you go on to Wikipedia, you'll find a million of these little mnemonics, and you can use whatever one makes the most sense to you. Okay, so in addition to sine, cosine, and tangent, we have 3 other trigonometric functions. Okay, and these are the cosecant, CSC of theta, the secant, SEC of theta, and the cotangent, COT of theta. And the cosecant is just the reciprocal of the sine. So it's going to be the length of the hypotenuse over the length of the opposite side. Okay, so that's going to be 1 over sine theta. Secant is going to be the reciprocal of the cosine. So it's going to be the length of the hypotenuse over the length of the adjacent side. Okay, and finally the cotangent is going to be the reciprocal of the tangent. So that's going to be the length of the adjacent side over the length of the opposite side. So one way you can remember cosecant, secant, and cotangent Hopefully sine, cosine, and tangent will be easy to remember using one of your mnemonics. For cosecant, secant, and cotangent, there's a very clear pairing here between cotangent and tangent. So they are reciprocals of each other. To remember the other four, you just want to recall that the function and its reciprocal are going to form a copair. So for example, we have cosine and secant. So one of these has a co in it, the other one does not. Similarly, we have cosecant and sine. So these two form a pair because we have a co and we have a non-co. So again, we have sine, cosine, and tangent. And then with the reciprocal, if the function does not have a co in it, the reciprocal will. If the function does have a co in it, like cosine, its reciprocal will not. And then again, tangent and cotangent should be pretty easy to remember. Okay, so those are our 6 trigonometric functions. Okay, so we can use these trig function definitions 2 different ways. The first is if we're given the sides of a right triangle, we can find the trigonometric functions of one of the acute angles in that right triangle. Okay, so for example, if we have a right triangle with legs of length 3 and 4, and whose hypotenuse has length 5. Now 3, 4, and 5 is an example of what's called a Pythagorean triple, which is 3 whole numbers that can form the lengths of the sides of a right triangle. There are not a whole lot of Pythagorean triples. It's going to be a good idea to have memorized some of the smaller triples, like for example 3, 4, and 5, because that way you don't have to use the Pythagorean theorem on these triples. And you can check 3 squared plus 4 squared is 9 plus 16 is 25, which is 5 squared. Okay, let's suppose that theta is an acute angle, the one that is opposite the side of length 3. Okay, so then, for example, sine theta is going to be the length of our opposite side, which is 3, over the length of our hypotenuse, which is 5. Okay, or for example, if we wanted cotangent theta, cotangent theta is going to be the length of the adjacent side, which is 4, over the length of the opposite side, which is 3, and so on and so forth. So if you're given all 3 of your sides for a right triangle, or if you're given 2 sides, you can find the third side using the Pythagorean theorem, and then you can just use the ratios of the sides. So this is a very side-centric way of doing trigonometry. Note that we have no idea what this angle theta is. When we get into inverse trig functions way down the road, we can figure out how to approximate this angle using a calculator, but we have absolutely no reference for what numerical value this angle theta has. But we don't need to know the value of theta to get its trig functions. Okay, now the other thing we can do with these definitions is to get values of the 6 trig functions for our special right triangles. Okay, so for example, let's say we have a 45, 45, 90 right triangle. Now, as I said in a previous video, if the lengths of the legs of a 45, 45, 90 triangle are 1, the hypotenuse has to have length square root of 2. So here we have the lengths of the sides of a 45, 45, 90 triangle. Now we could generalize this and do a square root of 2. It's not going to affect anything we do here with the ratios, because when we start dividing lengths of sides, the a's would cancel out anyway. So we may as well just use this particular right triangle. Okay, so now 45 degrees is going to be our angle theta. Okay, and I'm going to use the one down here. Doesn't really matter, but I'll use the one on the bottom. So then we get that the sine of theta, which in this case would be the sine of 45 degrees, it's going to be our opposite side, which is 1 over our hypotenuse, which is square root of 2. So the sine of 45 degrees is 1 over square root of 2. Now this is a perfectly acceptable way to write the sine of 45 degrees. It has a square root in the denominator. That's absolutely okay. I prefer to write the sine of 45 degrees this way, but when you're working in ALEKS, you may also see this with a rationalized denominator. So the other way we could write this would be to multiply the top and bottom by the square root of 2. That keeps it the same because you're just multiplying by 1. Okay, and the sine becomes square root of 2 over 2. Okay, similarly, the cosine of 45 degrees is 1 over square root of 2 because the adjacent side also has length 1, and that's the same as square root of 2 over 2. And again, whether or not you rationalize the denominator, turn it into a 2, or keep it at square root of 2, that is a completely aesthetic choice. But my preference is to keep the square root in the denominator just because it's fewer steps. Okay, and then finally the tangent of 45 degrees is going to be the opposite over the adjacent is 1 over 1, which is 1. Okay, so here we have the sine, cosine, and tangent of 45 degrees. And since we have the sine, cosine, and tangent, we can take the reciprocals and get the cosecant, the secant, and the cotangent. Okay, so the cosecant of 45 degrees will be the reciprocal of the sine, so that's going to be square root of 2. Similarly, the secant of 45 degrees is the reciprocal of the cosine, so that's going to be square root of 2. And the cotangent of 45 degrees is going to be the reciprocal of 1 is 1. Okay. Now we can do the same thing with our 30, 60, 90 triangle. Okay, so I'll remind you of the sides of the 30, 60, 90 triangle. Okay, so recall that if the short side, the one that's opposite the 30-degree angle, has length 1, the hypotenuse will have length 2, and the long leg will have length square root of 3. Okay, therefore, starting with the 30-degree angle, the sine of 30 degrees is going to be the length of the opposite side, which is 1, over the length of the hypotenuse, which is 2. Okay, so the sine of 30 degrees is 1/2. The cosine of 30 degrees is going to be the length of its adjacent leg, which is square root of 3, over the hypotenuse 2. And finally, the tangent of 30 degrees is going to be the length of the opposite side, which is 1, over the length of the adjacent side, which is the square root of 3. Okay, and then again, if we wanted to rationalize that denominator, we could multiply the top and bottom by the square root of 3, and it would become square root of 3 over 3. Not my preference, but you will see it that way in ALEKS. And then if we take the reciprocals, we're going to get the cosecant of 30 degrees is the reciprocal of the sine, so that's going to be 2. The secant is going to be the reciprocal of the cosine, so that's going to be 2 over the square root of 3. Okay, or We multiply the top and bottom by square root of 3. We'll get 2 root 3 over 3. And finally, the cotangent of 30 degrees is going to be the reciprocal of the tangent, which is square root of 3. Okay, so there we have the 6 trigonometric functions of the 30-degree angle. We can do the same with the 60-degree angle. So if we do that, the sine of 60 degrees is going to be square root of 3 over 2. Okay, so now note the roles of the opposite and adjacent sides switch. So now the opposite side of the 60-degree angle is the adjacent side to the 30-degree angle. So the sine is square root of 3 over 2. The cosine of 60 degrees is the adjacent side 1 over 2. Okay, the tangent is the opposite over the adjacent side, which is square root of 3 over 1. And then taking reciprocals, we get that the cosecant is 2 over square root of 3, or 2 root 3 over 3. The secant of 60 degrees is the reciprocal of the cosine, which is 2. And finally, the cotangent of 60 degrees is the reciprocal of the tangent, which is 1 over square root of 3. Okay, now I'd like for you to note some of the relationships between the trig functions of the 30-degree angle and the trig functions of the 60-degree angle. Now, it should be obvious there should be some relationships because we're dealing with the same 3 sides no matter which angle we're dealing with. But notice if we look at a trig function of the 30-degree angle, for example, the sine, it's going to have the same value as the cofunction of the 60-degree angle. So in other words, the sine of 30 degrees is equal to the cosine of 60 degrees. Okay, or to give you another example, the secant of 60 degrees is equal to the cosecant of 30 degrees. So if you take a trig function of one of these angles and you add co to it, you're going to get the cofunction of its so-called complementary angle, which is the other acute angle in the triangle. This is something we're going to look at in the next video. You should also note that everything I've done here has been in degrees, just because it's a little bit easier to do degrees when we're working with triangles. But these same trig values would also hold for the angles pi over 6, pi over 3, and then with the 45, 45, 90 triangle, pi over 4.